In our work, we first conduct an experiment with self-distillation architecture with multi-branches and utilize linear probing to check each branch's generalization ability. Then we find that deep neural networks have different preferences for long-tailed distribution according to depth. Based on the finding, we design a novel self-heterogeneous architecture to fuse different intermediate features with high-level features and enable knowledge transfer between any two branches. Through extensive experiments, our proposed method achieves state-of-the-art performance in long-tailed visual recognition. Real-world images often exhibit a long-tailed distribution. A small portion of classes contain large number of images while the rest of them only take up few images. As an imbalanced learning problem, long-tailed learning has drawn many attentions. There are many methods have been proposed towards long-tailed learning. Among them, resampling and cost-sensitive learning are the most common solutions. Current directions for long-tailed learning varies among decoupled or multi-stage training, mixture of experts, and contrastive learning and so on. Most methods mainly focus on balancing the classifier, and our motivation falls on a question. Does representation learning have different preferences with respect to the model depth? To find the answer to this question, we utilize special neural network architecture named the self-distillation model. Self-distillation is usually considered as transferring knowledge from the deep to the shallow in one model, resulting in a lightweight model. However, such architecture can be viewed as a multi-branch model for ensemble. Therefore, we borrow a common self-distillation architecture for the following experiment, but without knowledge distillation. We perform linear probing on long-tailed CVPR 100 with a trained multi-branch model to see if the model has preferences for long-tailed distribution according to depth. And then we collect each class's maximum accuracy on the test set achieved by experts. The results are shown in this histogram. We can find that the deep branch tends to well fit categories with fruitful data, while the shallow branch is able to perform better than the deep on certain tail classes. Based on this finding, we think encouraging different preferences is a new way to cope with long-tailed distribution. The previous finding shows that a network with branched of different depths has the ability to diversify the test results. However, self-distillation architecture cannot satisfy the good and diverse demand, as branches of shallow depth can only generalize well on specific classes. Therefore, we choose the mixture of experts as our solution. First, we propose a fundamental component named depth-wise knowledge fusion. It assigns different shallow features to different experts, and then it fuses high-level features from each expert with its assigned shallow intermediate features. We choose Audemars product to implement such fusion. After fusion features, we utilize knowledge distillation between any two experts to enable them transferring different information. Once we have mutual distillation, the side effect caused by long-tailed distribution and distillation cannot be ignored. The second largest logit is usually called the hardest negative, which is crucial in long-tailed learning, as it can be hard for model to distinguish from the actual class. To cope with this, we proposed our second component named dynamic knowledge transfer. We first split logits into target part and non-target part. Then we select the average maximum non-target logit and combine it with other maximum ones among experts into a grand teacher. After that, we execute non-target distillation between grand teacher and non-target logits from each expert. In this way, the hardest negative can be dynamically suppressed without directly affecting the target logit. Here is the overall architecture of our proposed method. To keep the original distribution untouched during knowledge transfer, the proposed method adopts decoupled training. We conduct experiments with the proposed method and achieve state-of-the-art on 4 benchmark datasets, which are long-tailed CVPR 100, long-tailed ImageNet, iNaturalist 2018, and long-tailed places. We also conduct experiments on the generalization ability of the proposed method, and we find that dynamic knowledge transfer can effectively help to reduce the hardest negative. Beyond that, we also conduct an ablation study on the number of experts and find that architecture with more heterogeneous experts can promote more. In all, our work proposed a self-heterogeneous architecture with diversity corresponding to the model depth and a novel knowledge distillation approach to mitigate the effect of the hardest negative.